Let me introduce the error function. The error function is another tool which shows up in the solution of heat equations or wave equations using Fourier transform. Now the error function looks like here as a function that goes from -1 to 1. Here's -1, here's 1, here's 0. It's a monotonic function. You might not have seen it before, but it is relatively popular, so it will be found in any of these standard programs like MATLAB or Maple or Mathematica or even Wolfram Alpha, etc. They all know what the error function is. So I would like to show you how this can be used in an example here. Example 9.4. Use convolutions, the error function, operational properties of the Fourier transform to solve the boundary value initial value problem on an infinite domain. ut is equal to 1 over 100 du by dx square, and the initial condition, which is also called f of x, is 100 and 50 and 0. So let's plot the initial condition just quickly. We go from -2 to 0 and then from 0 to 1. From -2 to 0 we are at 100, and from 0 to 1 we are at 50, and we are 0 otherwise. Okay. Now applying Fourier transform to the heat equation, we get u hat time derivative equals minus omega square divided by 100 u hat. Okay, we have done Fourier transform of the derivatives a few times, so that's what you get. And then solving this, you get an exponential where the exponent is exactly e to the minus omega square divided by 100 times t. And then here this f is the initial condition, or actually the Fourier transform of the initial condition. So give it a hat, initial condition hat. To get the original function u, we then apply the inverse Fourier transform with a factor 1 over 2 pi. And we have the inverse transform of a product, f hat times the exponential. So meaning the inverse transform becomes a convolution integral. And so we have the convolution of the inverse transform of e to the minus omega square t divided by 100 times f, the original initial condition. And now the inverse transform of the exponential e to the minus omega times a constant we have done already. So here on page 334 I do this integration once more. It uses substitution and integration by parts. But we also did this in the previous video in one of the lemmas. And so fast step becomes 10 root of pi over t e to the minus 25x squared divided by t. So I would just say see previous video where we have done this explicitly as well. Okay, so then we take this fellow, put it here. We keep the 1 over 2 pi as a factor, and then we have the convolution with f. So let's write out the convolution integral. This is the function f times the exponential with the shifted argument x minus s. Okay, and now f was this guy, right? 150 between -2 and 1. So then we can use that here. Okay, so then the first integral from -2 to 0, where f has a value 100. Second integral from 0 to 1, where f has a value 50. So far, so good. But now we would like to use the error function to write these integrals here. Let me remind you what the error function looks like. So the argument w is actually the upper bound of the integral. Okay, that's where the function depends on. So we would like to take these integrals down here. Sorry, I have to jump back again. Okay, where we have now a lower integral, so we can flip the integral, make it minus, and get an integral from 0 to -2. And here we have an upper argument 1. And so this is what we would like to get out for the error function. So we have some substitution to do. We introduce z to be 5x minus s divided by root t, and then dz is minus 5 divided by root t ds. Okay, so z is substituting the s. and we substitute the earlier integrations. Now we have done substitutions also, so you might have to sit down and do it on a sheet of paper. What you get is this. You get 100 over root pi. The integral boundaries change from 5x divided by root t to 5 times x plus 2 divided by root t, but then the exponential becomes simple, and then same exponential in the second bit, and the integration boundaries also have changed here. But then the first one would be the integral from 0 to 5x plus 2t, so that is this one, minus the integral from 0 to 5x divided by root t, the lower boundary. So then you can write this first integral as a difference of two arrow functions, but just playing with the boundaries and kind of substituting the 0 in the middle. Notice also the 100 becomes a 50 because here we have a factor 2, which we need for the arrow function. Okay. And then here this factor 50 becomes a 25 for the same reason. And for the second integral, again, we get a difference of arrow functions. The upper boundary makes this guy, and the lower boundary makes that guy. Okay? So I really recommend you sit down and do this example on a piece of paper. This is stuff which we will likely test in homeworks and in exercises.